In tropical climates, solar storms have allowed auroras to be seen in places like Mexico. Imagine standing in the peaceful Mexican countryside at night, looking up at the sky and seeing red clouds gently ripple as if the sunset had mistakenly returned. But in the middle of the night, that's already happened. In 1859, during the largest solar storm ever recorded, auroras were visible as far south as the Caribbean. This event was linked to the strongest coronal mass ejection ever observed, which caused widespread electromagnetic disruptions. Auroras are caused by charged particles emitted by the sun. These particles interact with Earth's magnetosphere, following magnetic field lines toward the poles. Once they reach the upper atmosphere, they collide with atoms, releasing energy in the form of light. The colors of the light depend on the gas and altitude. Normally this happens near the magnetic poles, but during a major solar storm, Earth's magnetic field is compressed. This allows the auroras to reach further, even toward the equator. This is why auroras were seen in places like Havana, Bogota, and possibly southern Brazil during the 1859 event. Records from that time describe a reddish sky, the failure of telegraph systems and electric shocks to operators, all signs of the extreme geomagnetic disturbance. At lower latitudes, the auroras appear differently. Instead of arching, moving structures seen near the poles, they appear as a diffuse glow across the horizon, often with a reddish hue. This happens because the aurora is high up at about 100 kilometers, but it is viewed from a shallower angle, which alters its appearance. The light passes through more of the atmosphere, which changes its color and spread. In addition to the 1859 event, auroras in mid and low latitudes were also seen in 1921, 1989, 2003 and 2023. These events are always linked to active solar cycles. During such events, the density of solar particles increases significantly, with intense flows of protons and electrons. The direction of the interplanetary magnetic field also plays a role in allowing these particles to penetrate Earth's magnetosphere. Nowadays, satellites like DSCO VR and ACE monitor the solar wind in real time, providing alerts up to an hour before high-speed particles head toward Earth. This gives satellite operators, power grids, and communication systems time to adjust, reducing damage during geomagnetic instability. Observing auroras outside the polar regions helps scientists refine physical models of Earth's magnetosphere. Data from these events help researchers understand how Earth reacts to sudden solar wind changes and how these reactions vary by latitude. This makes simulations of future extreme events more accurate, helping predict their effects on satellite systems and terrestrial networks. During these storms, the KP index, which tracks geomagnetic activity, often exceeds a value of 8, indicating strong instability. This results in intensified ring currents in the Van Allen radiation belts and deformed magnetic fields. These changes are directly linked to the auroras expanding into tropical regions and the appearance of phenomena like ground-induced currents. The frequency and intensity of these events follow the solar cycle, which lasts about 11 years. During solar maximums, the likelihood of storms that can create tropical auroras is much higher. The current solar cycle, number 25, is showing an increase in activity, with predictions indicating a peak around 2025. The occurrence of auroras at lower latitudes proves that under certain conditions of solar activity and magnetic orientation, solar particle impacts can extend beyond their usual range. These events offer valuable data and emphasize the need for continuous monitoring of space weather. The size of the South Atlantic Anomaly SAA is also increasing. This change is part of broader shifts observed in Earth's global geomagnetic field, with some researchers suggesting it might indicate a long-term geomagnetic reversal. While a full reversal isn't expected soon, historical records show that such flips have occurred many times in Earth's history. The weakening and instability observed in the SAA might be early indicators of deeper changes in Earth's geomagnetic processes. However, these changes take thousands of years, and their exact timing is uncertain. Earth's magnetic field plays a vital role in protecting the planet from solar wind and cosmic radiation. In regions like the SAA, where the shield is thinner, satellites and spacecraft naturally detect more energetic particles. The data gathered from these regions is valuable for space weather forecasting and radiation risk assessment. Several missions such as the Hubble Space Telescope, the Chandra X-ray Observatory, and ESA's swarm satellites have taken the SAA into account when planning their operations. The anomaly affects both the quality of data and the longevity of spacecraft in low Earth orbit. Engineers design special shielding and operational protocols to handle SAA encounters. The SAA highlights that space near Earth is not uniform. It reflects the dynamic nature of our planet's interior and magnetic environment. As we expand satellite networks and missions in orbit, understanding anomalies like the SAA becomes more crucial for both scientific exploration and safety. High above Earth, cosmic rays generate antimatter in the upper atmosphere, forming tiny bursts of positrons during solar storms. These bursts aren't from science fiction. They're the result of natural processes involving cosmic rays. When high-energy particles from space collide with atoms in Earth's upper atmosphere, they produce secondary particles, including positrons, which are the antimatter counterparts of electrons. This phenomenon is especially common during solar storms. When the sun emits intense streams of energetic particles, they trigger reactions in Earth's atmosphere that can lead to the creation of positron-electron pairs. This process has been detected by instruments on balloons, satellites, and space telescopes over the past 2 decades. Though the antimatter produced is short-lived, with positrons quickly annihilating when they meet electrons, their brief existence offers crucial insights into high-energy physics in near-Earth space. One of the first detections of this phenomenon came from NASA's Fermi Gamma-Ray Space Telescope, which observed bursts of gamma radiation above thunderstorms. These bursts were linked to terrestrial gamma-ray flashes (TGFs), which happen during intense lightning events. TGFs can accelerate particles upward with such force that antimatter is produced in the process. This unexpected connection between thunderstorms and antimatter creation revealed that Earth's atmosphere is an active site of high-energy physics, not just a passive recipient of cosmic particles. In some rare cases, positrons generated above storms travel back toward Earth along magnetic field lines. This has been observed by instruments like the Alpha Magnetic Spectrometer AMS-02 aboard the International Space Station (ISS). Positrons are also seen in connection with solar energetic particle (SEP) events. During these storms, the influx of high-energy protons enhances atmospheric collisions, increasing the production of antimatter. These observations help refine models of particle interactions and atmospheric conditions during extreme solar activity. While the amount of antimatter produced is small, nowhere near enough for practical use, its consistent detection near Earth is significant. It shows that antimatter isn't limited to distant astrophysical phenomena like black holes or pulsars. It can also be created in Earth's immediate environment under the right conditions. This is important both for fundamental physics and space weather research. Antimatter production serves as a natural tracer of particle acceleration and electromagnetic interactions in the atmosphere, and helps explain some high-energy gamma-ray signals detected by space-based observatories. Instruments such as Pamela, Agile, and AMS-02 have expanded our understanding of how Earth fits into the broader network of cosmic ray interactions. Their data show that even a planet with a protective magnetic field can host micro-events of matter-antimatter transformation triggered by both internal and external factors. These findings place Earth into the larger context of high-energy astrophysics and show that our planet is not isolated from cosmic events. Even in its upper atmosphere, the interaction between radiation, magnetism, and particles continues to produce extreme physical phenomena. Satellites like the Cluster mission and NASA's Themis probes track magnetic field strength and particle flow. These events can lead to localized increases in ionospheric density and current systems. The direct entry of solar particles heats the upper atmosphere, alters radio wave propagation, and can affect GPS accuracy. These variations are particularly important for communication systems in polar and subpolar regions, where the effects are strongest. Some magnetic holes are linked to high-speed solar wind streams or coronal mass ejections (CMEs). In these cases, a combination of intense solar wind pressure and favorable interplanetary magnetic field (IMF) orientation greatly increases the chance of solar particles entering Earth's atmosphere. These conditions are closely monitored by satellites positioned upstream in space. The ability of solar wind to penetrate the ionosphere through these gaps contributes to space weather phenomena, making it harder to predict geomagnetic activity. Because of their localized nature, these structures are essential targets for research in near-Earth space. Understanding where and when magnetic holes appear is key to understanding Earth's magnetosphere. This helps refine models of magnetic reconnection, a process seen in astrophysical plasma physics in events like solar flares and black hole accretion disks. As satellite constellations increase and polar navigation becomes more common, recognizing these magnetic weak spots becomes more crucial. These areas represent places where spacecraft might experience higher radiation exposure or communication disruptions, even during quiet space weather conditions. Magnetic holes show that Earth's magnetic field is not a uniform static shield. Instead, it is a dynamic system with localized instabilities that provide insights into the interaction between solar activity and Earth's electromagnetic environment. Earth's faint glow is visible on the Moon's dark side, especially when the Moon is a thin crescent. This subtle glow, called Earthshine, is the result of sunlight reflected off Earth's surface and clouds, which then bounces onto the Moon. It's most noticeable during the days around a new moon when Earth's disk is nearly fully illuminated, as seen from the Moon's surface. Earthshine is a form of secondary illumination. Just as the Moon reflects sunlight to Earth, Earth does the same to the Moon. Since Earth has oceans, clouds, and ice, it reflects a larger percentage of sunlight than the Moon does, making Earthshine visible even when only a small sliver of the Moon is lit by direct sunlight. The phenomenon has been known for centuries. Leonardo da Vinci was one of the first to explain it correctly in the 1500s. He realized that the light seen on the Moon during its crescent phases must be sunlight reflected from Earth's surface. This insight marked an early example of understanding Earth's system science. Earthshine is most noticeable when the Moon is closest to the Sun in the sky near a new moon, as this is when Earth appears nearly full from the Moon's perspective. From space, Earth's bright disk shines over 50 times more brightly than the full Moon does when viewed from Earth. This intense reflection bathes the lunar surface in a subtle but measurable glow. Modern instruments can quantify Earthshine and use it to study global reflectivity, also known as albedo. Observatories like the Big Bear Solar Observatory in California have used Earthshine to track how much light Earth reflects over time. Variations in albedo can indicate changes in cloud cover, polar ice, or vegetation, all of which affect the planet's energy balance. The speed of a coronal mass ejection, CME, directly impacts the strength of its shock front and the effects it has on Earth. When shock waves from a CME hit Earth, they compress the planet's radiation belts, changing the distribution of high-energy particles in orbit. Satellites passing through these areas, either during or after a shock event, may experience radiation spikes, temporary failures, or permanent damage. That's why satellite operators carefully monitor space weather alerts, especially during periods of solar activity. Solar shock waves are tracked by satellites positioned upstream from Earth, such as AC, Discover, and Wind. These spacecraft measure solar wind speed, density, and magnetic field characteristics in real time. When a shock is approaching, ground stations receive alerts about 30 to 60 minutes ahead, allowing a brief window for response. In addition to magnetic effects, solar shocks cause changes in Earth's ionosphere. The compression of Earth's magnetosphere allows energetic solar particles to penetrate deeper into the atmosphere. This increases ionization and disrupts high-frequency communications and GPS signals. These changes are especially noticeable in polar regions. Researchers use magnetohydrodynamic (MHD) simulations to model how charged fluids like plasma interact with magnetic fields, helping predict the arrival times, intensities, and consequences of solar shock waves based on solar observations. Understanding solar shock waves is crucial for space weather forecasting and protecting modern infrastructure. These shock waves are one of the fastest and most dynamic elements in solar-terrestrial interaction. They deliver energy to Earth's magnetic system in just minutes. Despite their short duration, these shockwave encounters play a key role in triggering space weather events. They mark the transition between calm and disturbed space conditions and often signal the start of more intense geomagnetic activity. Molecules such as hydrogen cyanide (HCN) and cyanogen (CN) are sometimes found in space. These compounds, often linked to industrial and biological toxicity, are also present in interstellar clouds, comets, and the upper layers of planetary atmospheres. Occasionally, small amounts of these molecules reach Earth and accumulate in the stratosphere. They arrive through various means, including micrometeoroids and cometary dust, which continuously bombard Earth's atmosphere. Additionally, some cyanides are formed when cosmic rays interact with nitrogen and carbon in Earth's atmosphere, triggering chemical reactions that create small amounts of HCN. Once formed or deposited, cyanide molecules can persist in the lower stratosphere for several days. This region, located between 10 and 50 kilometers in altitude, offers relatively stable conditions where vertical mixing is limited. As a result, volatile compounds like HCN can accumulate before eventually breaking down or dispersing. NASA's Microwave Limb Sounder (MLS) and the Atmospheric Chemistry Experiment (AC) satellites have detected hydrogen cyanide in the upper atmosphere. These observations reveal seasonal and latitudinal variations in its concentration, with higher levels often appearing after meteor showers or during solar storms, which enhance particle influx and chemistry. While the presence of cyanide in Earth's atmosphere isn't harmful to life at ground level due to the extremely low concentrations, it provides valuable scientific insight. It serves as a tracer for high-altitude atmospheric chemistry, particularly in terms of how external particles interact with Earth's atmosphere. Cyanide-bearing molecules also help researchers study stratospheric circulation. By monitoring how HCN is transported and removed, scientists gain a better understanding of large-scale atmospheric dynamics, including how materials move between hemispheres and across different latitudinal zones over time. While hydrogen cyanide can also be produced from volcanic eruptions, biomass burning, and lightning, its extraterrestrial origin is supported by its association with meteor influx periods and isotopic ratios consistent with space-based sources. The persistence of these molecules in the stratosphere is driven by sunlight-induced photolysis and chemical reactions with hydroxyl radicals. Over time, these processes break down cyanide molecules into simpler compounds, which are then washed out of the atmosphere or integrated into broader carbon and nitrogen cycles. Studies of extraterrestrial cyanides on Earth offer insights into the delivery of organic materials from space. Molecules like HCN are considered precursors to amino acids and other prebiotic compounds. Their presence in Earth's atmosphere provides a modern analogue for the chemical processes that might have occurred on early Earth. During major solar storms, Earth's magnetic field doesn't just fluctuate, it creates electric currents in the ground. These are called geomagnetically induced currents, GICs, which occur when solar plasma disturbs Earth's magnetosphere. When a coronal mass ejection (CME) reaches Earth, it compresses the magnetosphere and induces rapid changes in the geomagnetic field. According to Faraday's law, these changes generate electric fields on Earth's surface, which drive GICs through power grids, pipelines, and even the Earth's crust. GCs typically follow paths of low resistance, particularly along long metallic structures like high-voltage transmission lines and oil pipelines. When GCs enter power grids, they can overload transformers, trip circuit breakers, and in extreme cases, cause permanent damage. This is a major concern for infrastructure operators, especially in high-latitude regions. The March 1989 geomagnetic storm in Quebec is one of the most well-known examples where GCs caused a blackout that lasted over 9 hours and affected millions of people. Similar events have been recorded in Scandinavia, South Africa, and the United States, although many of these were mitigated by improved design and monitoring. Regions with highly conductive rock layers such as clay, shale, or water-saturated soil are particularly vulnerable to GICs. These geological conditions amplify the strength of the currents. Ground conductivity maps are now used in risk models to identify where infrastructure is most exposed to geomagnetic hazards. Real-time satellite data and ground magnetometers help track the potential for GICs. When a solar storm is detected, operators may reconfigure power loads, reduce capacity on specific lines, or temporarily isolate transformers to prevent widespread failures and reduce the need for costly repairs. In addition to power systems, GICs also affect undersea cables, rail networks, and corrosion rates in long pipelines. In pipelines, GICs accelerate electrochemical reactions, leading to localized corrosion and structural damage over time. Monitoring stations now track voltage offsets to detect such anomalies early. During major solar storms, the Van Allen radiation belts also produce high-frequency radio noise. Known as chorus waves, these emissions result from the interaction between fast-moving electrons and the surrounding plasma. These waves play a role in accelerating particles and causing losses, creating a feedback loop that prolongs the storm's effects. Monitoring the radiation belts helps scientists understand how energy flows within Earth's magnetosphere. The belts act as temporary reservoirs, storing solar energy before it either dissipates into the atmosphere or escapes into space. This dynamic behavior is important for predicting long-term space weather patterns. To simulate how radiation belts evolve during solar activity, researchers use models like VERB and DREAM. These models assist in forecasting radiation conditions for satellite operators, astronauts, and mission planners. Their accuracy relies on continuous data from instruments that measure particle flux, magnetic fields, and wave activity. The belts also produce optical emissions when particles precipitate into Earth's upper atmosphere, triggering auroras especially near the poles. This connection between radiation belt dynamics and auroral displays links space phenomena with visible effects in Earth's sky. The Van Allen belts aren't static barriers. They are active, responsive regions in Earth's space environment. Solar storms transform them into glowing rings of high-energy particles, reshaping their structure and intensity. These changes provide a real-time record of how solar activity affects Earth's environment just beyond our atmosphere. Earth's celestial poles move in a 26,000-year cycle. The stars we see in the night sky aren't fixed forever. Over thousands of years, Earth's axis slowly wobbles in space, a movement known as axial precession. This motion causes the celestial poles and equinox positions to drift across the sky, completing a full cycle every 26,000 years. Axial precession occurs because of gravitational forces from the Moon and the Sun, which act on Earth's equatorial bulge. Since Earth isn't a perfect sphere, it's slightly flattened at the poles and wider at the equator. These forces cause the rotation axis to trace a slow circular path in space, much like a spinning top wobbling as it turns. Currently, Earth's axis points toward Polaris, making it our North Star. However, 5,000 years ago it pointed closer to Theban, a star in the Draco constellation. In about 12,000 years the axis will point near Vega in the Lyra constellation. This shift means the North Star changes over time. Axial precession also affects the position of the equinoxes, the points where Earth's equator intersects the Sun's orbital plane. As these points shift westward along the ecliptic, the background constellations change with the seasons. Ancient astronomers noticed this shift, and Hipparchus, a Greek astronomer in the 2nd century BCE, was the first to quantify it by comparing star positions over centuries. His observations showed that the positions of stars relative to the seasons had shifted, prompting further study of long-term sky movements. Today we account for axial precession in astronomical calculations, calendars, and space navigation. It slightly changes the timing of solstices and equinoxes and alters star charts used by observatories and spacecraft. Modern missions like Gaia track this motion with great precision. Precession also affects long-term climate cycles. Over tens of thousands of years it shifts Earth's hemisphere's orientation toward the Sun during different seasons. This is part of the Milankovitch cycles, orbital patterns that influence Earth's glacial and interglacial periods. The rate of axial precession is about 50 arcseconds per year, which adds up slowly. After 26,000 years, Earth's axis completes a full cycle, returning to its original position. This movement doesn't change Earth's tilt, it simply shifts the direction the tilt points. Astronomers and historians use models of precession to reconstruct ancient skies. These models help date events like eclipses, alignments, and even archaeological structures built to match specific star positions. Precession connects modern science with ancient observations over millennia. Earth's slow wobble is imperceptible within a single lifetime, but over centuries and millennia, it changes our view of the cosmos. The stars above us don't move, rather Earth's position relative to them shifts. Not all lightning stays near the ground. High above powerful thunderstorms, rare and brief flashes of light occur, known as sprites, elves, and blue jets. These electrical phenomena were once considered folklore, but have since been confirmed through observations by satellites and cameras. Sprites are red-orange glows that occur 50 to 90 kilometers above thunderstorm clouds. They appear in clusters, often shaped like jellyfish or columns, and last only a few milliseconds. Sprites are triggered by strong lightning strikes that create powerful electric fields in the upper atmosphere. Elves, an acronym for emission of light and very low-frequency perturbations, occur even higher, forming expanding rings of light about 100 kilometers above the ground. These flashes last less than 1,000th of a second and result from the electromagnetic pulses generated by lightning traveling through the ionosphere. These flashes are not usually visible from the ground under normal conditions, but they were first detected accidentally in space footage or by cameras positioned above storm systems. Since then, dedicated observation programs using low-light cameras, aircraft, and satellites have captured thousands of events worldwide. Sprites and elves occur far above the cloud tops and don't directly affect the ground, but they demonstrate how energy from thunderstorms can travel upwards into the mesosphere and ionosphere, regions that are critical to radio communication and space weather interactions. Blue jets are another related phenomenon, appearing as narrow cones of blue light rising from the tops of thunderclouds to altitudes of about 50 kilometers. Unlike sprites and elves, blue jets travel directly from the cloud into the stratosphere, driven by charge imbalances inside the storm. These upper atmosphere flashes are part of a broader system called transient luminous events, TLEs. TLEs represent the vertical transfer of energy from the lower atmosphere into space. They're not rare, but they're difficult to detect due to their speed, altitude, and specific viewing conditions. NASA missions like ISIL aboard the Formosat 2 satellite and the ASIM instrument on the ISS have provided high-resolution recordings of these flashes, helping scientists understand their structure, origin, and frequency. Some studies suggest that sprites and elves may contribute to nitrogen oxide production in the upper atmosphere, which could influence ozone levels. While the overall effect is minor, their role in upper atmosphere processes continues to be explored. These high-altitude lightning phenomena show that thunderstorms extend their energy far beyond Earth's surface. Their energy reaches into the atmosphere, connecting weather systems with space, where light, plasma, and electricity interact in brief, spectacular bursts. Tides do not generate enough pressure on their own to trigger eruptions in stable volcanic systems. Researchers use models to simulate how tidal forces interact with magma chambers and fault lines. These models factor in rock mechanics, elastic deformation, and fluid dynamics to predict how stress changes at different depths. GPS and satellite interferometry confirm that Earth's surface shifts in sync with the lunar tides. The influence of tides on seismic activity has been documented. Some earthquake swarms and tremors near volcanoes occur during certain tidal phases, supporting the idea that tidal forces influence both magma movement and the mechanical behavior of faults and fractures in active volcanic systems. In addition to the moon's influence, solar tides also play a role, though their effect is weaker. The combined effect of both lunar and solar tides produces cycles of constructive and destructive interference known as spring and neap tides. These cycles might affect geological processes more significantly during peak tidal alignments. Volcanic gas emissions such as sulfur dioxide and carbon dioxide have shown small variations based on tidal timing. By monitoring these emissions, scientists can connect subsurface activity to external tidal cycles, which aids eruption forecasting models. Not all volcanoes react to tidal forces, and the impact varies depending on geological structure, magma composition, and tectonic setting. However, the relationship between tides and volcanism proves that Earth's internal processes are influenced by external gravitational forces. This connection between celestial mechanics and Earth's dynamics shows how planetary bodies stay physically connected through subtle forces. Earth's internal activity, while primarily driven by heat and pressure, resonates with the Moon's rhythm. Earth's crust rises and falls daily. The solid ground moves up to 30 centimeters due to the Moon's gravitational pull. The Moon creates tides not just in Earth's oceans, but in the solid surface as well. This effect, called earth tide or body tide, causes rhythmic vertical movement of the crust, up to 30 centimeters twice a day. Though invisible to the naked eye, this constant flexing impacts geophysics, satellite positioning, and even seismic activity. Earth tides occur because the Moon's gravity stretches the planet along the Earth-Moon axis. At any moment, the surface beneath the Moon is pulled slightly upward, as is the point directly opposite. The crust bulges outward, while areas perpendicular to this line are compressed. The degree of this deformation depends on the alignment of the Moon and Sun, local geology, and latitude. During spring tides, when the Moon and Sun align, the largest vertical shifts occur. In contrast, neap tides generate smaller, less noticeable movements. These vertical shifts are measured by highly precise instruments like superconducting gravimeters, laser ranging systems, and Global Navigation Satellite System (GNSS) receivers. Earth tides are essential for correcting satellite orbit data and refining measurements of Earth's shape and movement. They also affect the stress state of faults and rock layers. In some areas, increased seismic activity has been linked to specific tidal phases. This is most noticeable in regions already experiencing tectonic stress, where small tidal changes can trigger low-magnitude earthquakes. In underground labs and particle physics experiments, Earth tides must be accounted for to maintain precise calibration. Changes in Earth's crust, even those as small as a centimeter, can impact sensitive measurements over time, especially for interferometers and gravity wave detectors like LIGO. Researchers model Earth tides using elastic Earth theory, which treats the planet as a flexible body responding to gravitational forces. These models incorporate parameters such as love numbers and elastic moduli, which describe how Earth compresses or expands in response to tidal forces. Beyond vertical movement, Earth tides also cause small horizontal shifts, altering the spacing between points on the surface. Over time, these shifts accumulate and can be tracked to study continental movement and deformation patterns. In this way, Earth tides contribute to long-term tectonic monitoring. The phenomenon also affects deep boreholes where sensors detect changes in fluid pressure and rock strain in sync with tidal cycles. These measurements provide insights into subsurface fluid movement and reservoir behavior important for geoscience and energy extraction. Although Earth tides are subtle, they are a constant reminder that the ground beneath us isn't static. The Moon's gravitational pull keeps Earth in continuous motion, reshaping its surface by small degrees every day. This daily rise and fall of the crust, driven by celestial forces, links Earth's interior with the movements of its nearest neighbor, the Moon. Orbiting satellites detect a persistent stream of low-frequency electromagnetic noise, a phenomenon sometimes referred to as the clarinet of space. This persistent magnetic hum originates from natural interactions between Earth's magnetic field and surrounding plasma. The noise primarily consists of ultra-low frequency ULF waves, which range from 1 MHz to a few hertz. These waves are generated by various processes, including solar wind pressure, magnetosphere instabilities, and dynamic currents in the ionosphere. The result is a background hum of magnetic energy that permeates the near-Earth space environment. Satellites like the ESA Swarm mission and NASA's Themis probes carry magnetometers that record these oscillations continuously. The data they provide reveal wave propagation patterns, resonance and damping as these ULF waves travel along magnetic field lines from the magnetosphere to Earth's surface and back. Some of these waves are global standing waves, known as field line resonances. They form when magnetic field lines oscillate at their natural frequencies, like strings plucked in space. These resonances depend on the length of the magnetic field line and the plasma density along its path, producing frequencies unique to each location. The magnetic hum is also influenced by Earth's rotation, internal electrical currents and fluctuations in solar wind. When solar wind pressure increases or changes direction, it excites additional wave activity. These interactions create a rich and evolving electromagnetic environment that satellites must operate within and account for. Ground-based magnetometers also detect these same waves, though they are often filtered by the conductivity of Earth's crust. By combining space-based and surface data, researchers can model how electromagnetic energy moves between Earth and space, and how it varies during geomagnetic storms and quiet periods. ULF waves can affect satellite operation by causing fluctuations in onboard magnetic sensors and potentially inducing currents in long spacecraft structures. They also help transfer energy from the magnetosphere to the ionosphere, where they accelerate charged particles downward into Earth's atmosphere. ULF waves are also used as natural probes in space weather studies. By analyzing their frequency and behavior, scientists can infer properties of the magnetosphere, such as plasma density, magnetic field strength, and the presence of instabilities. This method complements direct particle measurements. In addition to scientific research, these electromagnetic signals have practical applications, such as locating mineral deposits and studying deep Earth conductivity. Their propagation through Earth's crust provides a non-invasive way to probe underground structures at regional and continental scales. The continuous magnetic hum of Earth is a fundamental feature of its geospace environment. Though it's silent to human ears, it provides essential data for understanding how energy moves through and around the planet. From its outer magnetic shield to the surface below, electric fields link Earth's surface to space. Earth is part of a vast electrical circuit that extends all the way into space. This global electric system, known as the Earth ionosphere-magnetosphere coupling, involves continuous exchanges of electrical charge between the planet's surface, atmosphere, and magnetic field. At the surface, Earth carries a net negative electric charge, while the ionosphere is positively charged. Between them exists a vertical electric field, typically around 100 volts per meter near the ground, maintained by thunderstorms and electrified clouds that act as natural generators. Each day, thousands of thunderstorms transfer charge upward through lightning and upward currents. These local discharges combine into a global pattern known as the atmospheric electric circuit. The result is a continuous flow of current, about 1,800 amps in total, moving between the surface and ionosphere. Beyond the ionosphere, this circuit connects to the magnetosphere through field-aligned currents, also known as Birkeland currents. These streams of electrons and ions follow magnetic field lines from the poles into space, linking Earth's weather-driven electrical activity with its outer magnetic field dynamics. These currents can grow stronger during geomagnetic storms and help control auroral activity. In addition to vertical currents, horizontal electric fields also develop in the ionosphere, especially during space weather events. These fields spread charge across the globe and affect radio wave propagation, satellite drag, and ionospheric density. They also contribute to the creation of electric fields on the ground through electromagnetic induction. The connection between Earth and space is two-way. Just as atmospheric processes impact the magnetosphere, space weather, such as solar flares and the impact of CMEs, sends charged particles and electromagnetic waves into the ionosphere. These waves change its conductivity, which affects how current flows through the entire system. Researchers have created models using equations to simulate this system, accounting for conductivity, charge separation, and plasma behavior. These models are vital for predicting satellite charging, communication disruptions, and changes in electric fields on the ground during space weather events. Understanding this global circuit bridges the gap between atmospheric science and space physics. It shows how processes that happen hundreds of kilometers apart, like cloud electrification and auroral current systems, are all part of a single dynamic system. Earth's electric connection to space is an ongoing measurable phenomenon. From lightning strikes to polar currents, it shows that Earth's surface, atmosphere, and magnetic field are all part of one connected electrical environment, extending far beyond the clouds. Solar storms heat the upper atmosphere. When intense solar storms hit Earth, their impact goes beyond auroras and magnetic disturbances. One subtle but significant effect is the heating of the thermosphere, the outermost layer of Earth's atmosphere. This heating causes the atmosphere to expand outward, sometimes reaching or exceeding the altitude of the International Space Station (ISS). Solar storms release huge amounts of energy into the magnetosphere and ionosphere. Charged particles and electromagnetic waves interact with atmospheric gases, exciting them and increasing their temperature. The thermosphere, which starts around 90 kilometers above Earth, expands as its kinetic energy increases. During strong geomagnetic storms, this expansion can increase atmospheric density at altitudes of 300 to 500 kilometers, exactly where many satellites and the ISS orbit. This added density creates drag on spacecraft, slowing them down and causing orbital decay. Mission operators need to monitor this carefully to adjust satellite trajectories and prevent early re-entry. The heating effect isn't the same everywhere. It depends on factors like latitude, time of day, and the intensity of solar input. The most dramatic changes typically occur near the poles, where solar wind energy penetrates deeper along magnetic field lines. However, during extreme solar events, the expansion can affect Earth's atmosphere globally. One well-known example happened in March 1989 when thermospheric density increased so much that satellites experienced unexpected drag. In response, satellite designers began factoring solar activity forecasts into their operational plans. Real-time space weather alerts now help reduce risks of orbital instability during storms. The heating also impacts the distribution of ions and electrons in the ionosphere, which can disrupt radio communications, GPS signals, and satellite tracking. These effects are especially noticeable during intense solar maximum periods, which occur roughly every 11 years. Instruments like accelerometers on satellites and ground-based radar provide real-time measurements of atmospheric drag and density. Missions like NASA's TIMED and ESA's GOES have helped create detailed models of thermospheric behavior under various solar conditions. These models are essential for predicting drag and protecting orbital systems. The thermosphere's expansion and contraction are responses to space weather, and once a storm subsides, the thermosphere gradually cools and contracts, often taking several days. This thermal inertia creates lingering effects that continue to influence satellite orbits even after solar activity returns to normal. Beyond operational concerns, studying thermospheric heating helps researchers understand energy transfer in Earth's near-space environment. It shows how solar energy moves downward, interacts with atmospheric elements, and affects long-term climate dynamics in the upper atmosphere. The sun-driven expansion of the thermosphere is a prime example of how space weather impacts Earth's extended environment. It links solar activity directly to the functioning of human-made systems in orbit, requiring continuous monitoring to keep space operations safe and stable. The stratosphere, located between 10 and 50 kilometers above Earth's surface, is considered too harsh for life. With low pressure, high UV radiation, and freezing temperatures, it doesn't seem like a place for living organisms. Yet, scientists have repeatedly detected viable microorganisms at altitudes above 20 kilometers, showing there's an active exchange between Earth's surface and its upper atmosphere. Experiments using balloons and high-altitude aircraft have found bacterial spores, fungal cells, and even DNA fragments in the lower stratosphere. These organisms are often dormant, adapted to extreme conditions, and capable of surviving intense desiccation and radiation. The exact source of these microbes is still unclear. Many are probably lifted from Earth's surface by strong atmospheric currents, volcanic eruptions, or large weather systems. Dust storms and cyclones carry particles, including microbes, high into the troposphere, where they eventually reach the stratosphere. Once they're in the stratosphere, these organisms can stay suspended for days or even weeks. The cold and low pressure slow their metabolic activity, allowing some bacteria to enter a spore-like state and survive. These microbes' protective outer layers, pigmentation, or DNA repair mechanisms help them resist UV damage. Some of these microorganisms eventually fall back to Earth with rain. Rain events pull particles from the stratosphere, including viable microbes, back to the surface. This cycling process may affect microbial distribution, ecosystem behavior, and even atmospheric chemistry. Methods like high-altitude filtration systems, impact collectors, and fluorescence-based biosensors are used to detect and study these microbes. NASA, ISRO, and other space agencies have conducted multiple missions to study this airborne microbiome. These findings suggest that life can survive in Earth's stratosphere, and similar environments on planets like Mars or Venus might also support microbial life, especially in transient airborne niches. The presence of these microorganisms at such high altitudes also challenges our understanding of the boundary between life and the upper atmosphere. It suggests that the biosphere extends further into Earth's atmosphere than previously believed, reaching into the stratosphere through natural atmospheric processes. These high-altitude organisms provide a glimpse of an active biological layer far above Earth's surface. Whether carried upward by storms or brought down with rain, these microbes represent the continuous movement of life between Earth's surface and the sky. These models help explain how tidal patterns change depending on latitude, season, and solar activity, and why they show stronger effects in regions with mountains or warm ocean areas. Long-term satellite records reveal that the strength and behavior of thermal tides vary with the solar cycle. During times of high solar activity, increased UV and X-ray radiation enhance heating in the upper atmosphere, which intensifies the tidal response and changes its vertical structure. These findings show that Earth's atmosphere is not stable but dynamically reacts to the sun's daily rhythm. The entire planet moves with solar energy, a subtle global oscillation that impacts both the space above and the weather below. Jet streams, fast-moving winds in the upper atmosphere, are influenced by the solar cycle. These winds help guide weather patterns around the globe. However, they also show a surprising sensitivity to solar activity. Decades of observations have shown a connection between jet stream behavior and the sun's 11-year solar cycle. Jet streams form near the boundaries of major air masses, usually around 10 to 15 kilometers above the Earth's surface. The most notable jet streams are the polar and subtropical jets, which travel faster than 100 kilometers per hour and affect storm paths, precipitation, and temperature patterns. During solar maxima, which are periods of high sunspot and solar flare activity, the sun produces more ultraviolet and extreme ultraviolet radiation. This extra energy heats the stratosphere, changing the temperature difference between the equator and the poles. As a result, jet streams shift in both speed and latitude. One observed effect is the strengthening of the polar night jet, which is a wind belt that surrounds the winter pole. During solar maxima, this jet becomes stronger, changing the structure of the stratospheric polar vortex and affecting the downward movement of atmospheric waves. These solar-induced changes can ripple downward, altering weather patterns in the lower layers of the atmosphere. For example, during certain solar maxima, the subtropical jet moves toward the equator or shows more zonal symmetry. These shifts can influence rainfall, storm intensity, and even the likelihood of sudden stratospheric warming events. The quasi-biennial oscillation QBO, which involves a periodic reversal of equatorial stratospheric winds, is also influenced by solar activity. The timing and strength of the QBO phases seem to change slightly depending on the phase of the solar cycle, showing another layer of sun-atmosphere connection. Satellite missions like AURA, COSMIC, and MEA reanalysis datasets have helped track long-term jet stream variations. These data confirm that jet stream characteristics such as speed, altitude, and variability are subtly affected by solar radiation over many years. Climate models help simulate how solar activity affects the upper atmosphere and spreads to lower layers. These models include factors like radiative transfer, interactions between waves and flows, and chemical feedbacks to understand the links between solar activity and large-scale wind patterns. While solar activity is just one factor influencing jet streams, its consistent correlation with the solar cycle offers valuable insights for long-range weather forecasting and atmospheric dynamics. The connection between solar cycles and high-altitude winds shows how solar changes ripple through Earth's atmosphere, from ultraviolet heating in the stratosphere to shifts in jet stream positions. The sun's rhythm quietly shapes the movement of air thousands of kilometers below. Earth's albedo, or reflectivity, is about 30%. This is the fraction of incoming solar radiation that Earth bounces back into space. Earth isn't just a planet, it's a source of light. This reflected light can be seen during the new moon phase. Earth's albedo varies depending on surface type, cloud cover, and atmospheric conditions. Bright surfaces like ice, snow, and thick clouds reflect more sunlight, while oceans and forests absorb more sunlight and reflect less. These variations combine to form a global average albedo of about 0.3. One notable example of Earth's albedo is Earthshine, the faint glow on the moon's dark side during the new moon phase. When Earth is fully illuminated from the moon's perspective, its reflected light softly lights up the part of the moon not directly lit by the sun. This glow can be seen from Earth with the naked eye, under clear conditions. Earthshine has been observed for centuries, but modern instruments allow scientists to measure its brightness and use it to study Earth's climate. Variations in Earthshine reflect changes in global cloudiness, aerosol levels, and surface reflectivity, offering a natural way to track Earth's energy balance. Satellites like NASA's Ceres and ESA's EarthCare missions measure Earth's albedo continuously. These instruments use radiometers to track how much solar energy is reflected versus absorbed. This data feeds into climate models and helps scientists understand how Earth's energy budget responds to changes in greenhouse gases and surface conditions. Albedo also affects global temperature. A higher albedo means more solar energy is reflected away, cooling the planet, while a lower albedo results in more energy being absorbed, leading to warming. Feedback loops like ice cover and cloud changes can amplify these effects, especially in polar regions. Seasonal changes and major weather events can temporarily alter Earth's albedo. For instance, large volcanic eruptions release reflective particles into the atmosphere, increasing albedo for months. Similarly, widespread snow cover during winter raises albedo across continents. In Earth system models, albedo is a key parameter for simulating long-term climate dynamics. It affects not only surface temperature, but also atmospheric circulation, precipitation patterns, and ocean currents by redistributing heat. Observing Earth from space shows its status as both a light source and a complex thermodynamic system. The sunlight it reflects isn't just a glow, it's a measurable dynamic signal that connects the planet's appearance with its physical processes. Albedo transforms Earth into a visible presence in the sky, even during the moon's darkest nights. It serves as both a scientific tool and a reminder that Earth, like the moon and other planets, reflects the light from the star that sustains it. Earth's magnetic field is not uniform. While the global geomagnetic field shields the planet from solar radiation, certain regions, especially over continental crust, have localized magnetic anomalies. These variations influence how solar particles interact with Earth's atmosphere and space environment. Continental magnetic anomalies are linked to variations in Earth's crust composition and structure. Large iron-rich formations such as ancient shield areas produce localized magnetic highs. These regions can slightly change the orientation and intensity of magnetic field lines, affecting how charged particles from the solar wind are directed toward or away from the surface. One effect of these anomalies is the localized intensification of energetic particle fluxes in the upper atmosphere. Areas with concentrated magnetic gradients can funnel or scatter particles in unusual ways, sometimes increasing exposure to solar and cosmic radiation in specific orbital zones above them. Satellites passing through these regions often record elevated radiation levels. These enhancements are distinct from larger geomagnetic structures like the South Atlantic anomaly, which is linked to the offset of the geomagnetic dipole. Instead, continental anomalies affect radiation belts and particle trajectories on smaller regional scales. High-resolution magnetic maps from satellites like Swarm and Orsted have revealed fine-scale features in Earth's crustal magnetic field. Researchers use this data to model how these features influence near-Earth particle dynamics and satellite safety. Radiation dose models for low Earth orbit missions now include crustal anomalies as part of risk assessments. Although the effect of these anomalies is smaller compared to global geomagnetic structures, they contribute to cumulative radiation exposure for satellites that frequently pass through specific latitudes or altitudes. These magnetic features also interact with ionospheric currents, impacting the distribution of electric fields and plasma density. During geomagnetic storms, the amplification of these currents can intensify ionospheric disturbances above specific continental regions, affecting communication systems and increasing satellite drag. Researchers use simulations to model how particle paths and radiation belts respond to changes in magnetic structures. These models show that small adjustments in field strength and orientation can change the way trapped particles are accessed, influencing how energy is distributed in near-Earth space. Understanding the magnetic anomalies on Earth helps improve space weather predictions, and this knowledge is crucial for planning satellite paths, radiation shielding, and high-altitude flight routes. It also gives us a better understanding of the connection between Earth's crust, magnetic field, and the solar environment. The localized magnetic features remind us that Earth's protective magnetic shield is not uniform but consists of a complex layered structure. These variations affect how Earth interacts with solar radiation, providing a more detailed understanding of the boundary between Earth and space than previously thought. Meteors leave behind seismic signals when they impact the Earth. These impacts create measurable ground tremors. While most meteors burn up before reaching the surface, those that make it through can cause seismic waves, similar to the tremors produced by earthquakes. These impact tremors can be detected by seismic networks, offering valuable insights into the impact and Earth's response. The force of the impact depends on the meteor's size, speed, and entry angle. Even small meteoroids, if they are dense and moving fast enough, can generate localized shock waves when they hit the ground. These shock waves travel as seismic energy, creating tremors that can be recorded by seismometers many kilometers away. A well-known example is the 2013 Chelyabinsk meteor. Though it exploded in the atmosphere, the shock wave was strong enough to hit the ground, creating seismic signals that were detected across Russia. Smaller meteor impacts have also been observed, with seismic data helping pinpoint their location and estimate the energy released. Seismic waves from meteor impacts are different from those caused by tectonic earthquakes. They have distinct frequencies and wave patterns, which allows analysts to tell their origin, even when there is no visual confirmation. Seismic networks now help detect meteor impacts along with other methods like infrasound, satellite images, and eyewitness reports. By combining seismic and acoustic data, scientists can reconstruct the meteor's trajectory, speed, and fragmentation pattern. Meteor impacts in ocean or soft sediment areas might produce weaker seismic signals, but they can still be detected if the event is significant enough. In some instances, these impacts have triggered small tsunamis or caused ground liquefaction, depending on local geology. Studying seismic data from meteor impacts also aids in planetary science. Seismometers placed on the Moon and Mars are designed to detect similar impacts, helping to estimate the frequency of meteoroid strikes and the internal properties of those planets. Earth-based techniques assist in validating data from other planets. Meteor-related seismic data also contribute to hazard assessments and public safety measures. Although large impacts are rare, the ability to detect and understand them in real time helps improve preparedness. The seismic tremors from these extraterrestrial impacts serve as evidence that Earth is still vulnerable to interplanetary debris. Volcanic eruptions have effects that reach deep into the atmosphere. Some of the largest eruptions can send ash, gas, and fine soot particles to heights above 50 kilometers, reaching the mesosphere. These high-reaching plumes can affect both atmospheric chemistry and space weather interactions. The altitude a volcanic plume can reach depends on factors like eruption intensity, gas content, and atmospheric conditions. Explosive eruptions that rapidly release magma create large, buoyant columns of gas and ash, which rise through the troposphere and stratosphere. In extreme cases, these columns can extend into the mesosphere. Eruptions like Mount Pinatubo, Hunga Tonga, and Krakatoa have sent plumes above 30 kilometers, with some even reaching as high as 55 kilometers. These eruptions inject massive amounts of material into the upper layers of the atmosphere, where particles can remain suspended for months or even years. At these altitudes, the air is thin and cold, slowing the dispersion of these particles. Soot and sulfur compounds can have a lasting impact on radiation balance and ozone levels, leading to global cooling effects and visual phenomena like enhanced sunsets and glowing twilights. High-altitude volcanic plumes also influence wind patterns and ionospheric conductivity. These changes affect the dynamics of the atmosphere and extend into near-space environments. Satellites, using instruments like thermal infrared sensors (LR) and UV spectrometers, monitor these plumes in real time. They track the plume's altitude, composition, and dispersion patterns. Volcanic plumes can also generate electrical activity. As ash particles collide and separate charge, they can produce lightning, sometimes reaching altitudes above 20 kilometers. This adds energy to the upper atmosphere and can trigger transient luminous events like sprites. Understanding how volcanic emissions behave at these high altitudes helps improve our models of Earth's radiative balance, chemical transport, and energy transfer processes. Volcanic plumes are not just regional hazards, they are global atmospheric events that affect Earth's interaction with space. At altitudes between 20 to 30 kilometers, in the lower stratosphere and ozone layer, small particles become suspended in stable air masses. Due to their size and chemical properties, these particles are perfect for absorbing ultraviolet, X-ray and gamma-ray photons from cosmic sources, including solar flares and distant astrophysical events. Laboratory tests and balloon instruments have confirmed that these particles react in unique ways when exposed to high-energy radiation. They can undergo ionization, emit secondary electrons, or trigger chemical reactions with nearby molecules. This has important implications for both atmospheric chemistry and radiation movement. Detection methods for these particles include optical spectroscopy, mass spectrometry, and advanced light scattering analysis. Recent high-altitude balloon and aircraft campaigns have collected samples showing altered energy states linked to cosmic photon interactions. These nanoparticles could affect ozone chemistry by interacting with chlorine and nitrogen compounds. Their role in radiation interaction may either boost or reduce processes that contribute to ozone depletion and formation. Though subtle, this influence is essential for refining our models of how the stratosphere behaves. In addition to their local chemical effects, these photoactive nanoparticles also impact how energy from space is absorbed and emitted in the atmosphere. This plays a key role in energy transfer, especially during times of high solar activity or an influx of cosmic rays. Researchers are exploring whether these particles contribute to the formation of noctilucent clouds or other mesospheric phenomena. Their ability to trap and alter radiation could make them potential sites for ice crystal formation at extreme altitudes. This study of cosmic photon interactions with atmospheric particles bridges the gap between atmospheric science and astrophysics. It shows that even in the cold, thin layers above the ozone layer, Earth's atmosphere is not static, but is actively interacting with cosmic radiation through particles that are invisible to the naked eye. Beneath Earth's surface, deep in the mantle, water exists in a hidden form. Minerals like ringwoodite contain traces of water from over 600 kilometers below the Earth's surface. This water isn't liquid but is bound within the crystal structures of deep mantle minerals. Ringwoodite, which forms under high-pressure conditions in the mantle's transition zone, 410 to 660 kilometers deep, is capable of storing hydroxide ions, water molecules broken into hydrogen and oxygen. This discovery of water in natural ringwoodite was confirmed by a rare diamond found in Brazil, which preserved the mineral and its trapped water. Estimates suggest that the transition zone could contain as much water as all of Earth's oceans combined, though it's chemically bound within the rock. This hidden water influences the mantle's viscosity, melting processes, and geodynamic activity. It affects how tectonic plates move, how magma forms, and how heat is transferred from Earth's interior. Even small amounts of water in the mantle can lower the melting point of rocks and change how materials behave deep inside, impacting volcanic activity and the movement of Earth's mantle. This water also plays a role in the deep Earth water cycle. As oceanic plates subduct into the mantle, they carry hydrated minerals which release water as they transform under pressure. This water can then travel upward, fueling volcanic eruptions and entering the surface system again. Seismic studies show variations in wave velocities that correspond to zones of hydrated minerals, confirming the presence of water in the mantle. High-pressure lab experiments and simulations with diamond anvil cells have helped confirm the mantle's ability to store water, shedding light on the Earth's complex inner structure. The existence of water so deep in the Earth changes our understanding of the planet's interior. It suggests a dynamic, interconnected system where water cycles through layers of solid rock hundreds of kilometers beneath the surface. Though this water is invisible and out of reach, it plays a significant role in the planet's long-term evolution, linking Earth's surface to its interior. In the outer core, deep beneath the mantle, a vast ocean of molten metal lies in motion, generating Earth's magnetic field. The outer core, which is primarily made of iron and nickel, extends from about 2,900 kilometers to 5,150 kilometers below the Earth's surface. The movement of this liquid metal is responsible for producing the magnetic field that protects the planet from solar and cosmic radiation. Despite the extreme pressures, the high temperatures of 4,000 to 6,000 degrees Celsius keep the metals in a liquid state. This creates an electrically conductive layer ideal for generating magnetic fields through the dynamo effect. The process begins with convection. Heat from the inner core drives the motion of the liquid metal. This motion, coupled with Earth's rotation, organizes into spiraling columns. As these moving charges create electric currents, magnetic fields are produced. The self-sustaining flow of liquid metal maintains a global magnetic field that extends far into space, forming the magnetosphere. This shield deflects solar wind, protects the atmosphere, and shields biological systems from high-energy particles. Fluctuations in this flow can cause changes in the magnetic field, including geomagnetic storms, pole drift, and even polarity reversals. Over the past century, Earth's magnetic north has shifted hundreds of kilometers due to changes in the core's dynamics. Seismic studies provide evidence for the outer core's liquid nature. Primary P waves pass through both solids and liquids, while secondary S waves cannot travel through liquids. The absence of S waves in specific depth ranges confirms the liquid state of the outer core. High-pressure simulations and lab experiments support this conclusion, confirming that iron alloys remain liquid under core pressures and temperatures. These interactions in the outer core influence surface phenomena, including tectonic motion and Earth's rotation. Small variations in angular momentum within the core can subtly affect Earth's rotation rate, creating measurable changes over time. Understanding the outer core is vital for predicting space weather, maintaining navigation systems, and modeling Earth's long-term stability. The outer core is a hidden engine that generates Earth's magnetic shield, connecting the planet's interior to its space environment. At sunset, satellites observe a faint green glow in Earth's upper atmosphere. This green light, detected by spectrometers on satellites, is a chemical signature of reactions in the thermosphere. Ultraviolet radiation from the sun breaks down molecular oxygen at altitudes around 90 to 100 kilometers, producing excited atomic oxygen. As these atoms return to their ground state, they emit photons, producing a green glow at a wavelength of 557.7 nanometers. This phenomenon, known as airglow, differs from auroras, which are caused by charged particles entering the atmosphere. Airglow occurs constantly and globally, but is most visible during twilight from space. Satellites like NASA's ICON monitor this glow to study atmospheric composition and energy exchange. The green emission serves as an indicator of oxygen density, temperature, and chemical processes in the upper atmosphere. The intensity of airglow increases at sunset as sunlight passes tangentially through the atmosphere. This increases photon scattering and excitation events, resulting in a brighter green glow observed at the edge of Earth as seen from space. The green signature also appears in limb-sounding instruments used to profile atmospheric layers. These measurements provide high-resolution data about the structure and behavior of the thermosphere and mesosphere, helping to refine global circulation models and space weather predictions. The glow varies with solar activity, latitude, and season, adding another layer of complexity to our understanding of Earth's upper atmosphere. During geomagnetic disturbances or times of increased solar activity, the brightness of these emissions can rise, affecting not just visibility but also how the upper atmosphere cools. Scientists are continuously studying how airglow interacts with other atmospheric phenomena, including gravity waves and irregularities in the ionosphere. These interactions provide clues about how energy moves through different layers of the atmosphere and how Earth's atmosphere reacts to external influences. The green glow seen from satellites is more than just a visual phenomenon. It serves as a diagnostic tool, helping researchers understand the chemical and physical processes happening in Earth's upper atmosphere, where sunlight interacts with air at the boundary of space. Earth also emits natural infrared light, which is detected by thermal sensors. Even at night, Earth radiates energy in the infrared spectrum, a type of light invisible to the human eye, but detectable by special instruments. This natural infrared emission is especially noticeable in areas with volcanic activity, where heat from below the surface escapes into the atmosphere. Volcanic zones are significant sources of infrared radiation. Lava flows, fumaroles, and geothermal vents all release substantial thermal radiation. Even inactive volcanoes can emit low-level infrared signatures due to underground magma movement or hydrothermal activity. Satellites equipped with thermal infrared imaging sensors, such as those from NASA's MODIS, Landsat, and ESA's Sentinel-3 missions, regularly scan Earth for thermal anomalies. These sensors detect radiation in the 3 to 15 micrometer range, wavelengths associated with heat being lost from the ground. These thermal signals help identify active lava fields, heated soil, and sudden temperature changes near fault zones. Natural infrared radiation is not limited to just volcanic areas. Cracks in Earth's crust and shallow magma chambers can subtly warm the surface as well. These small temperature changes, sometimes only a few degrees, are enough for space-based thermal sensors to detect. Earth's continuous emission of infrared light is a key part of its energy budget, helping maintain thermal balance. Volcanic areas contribute localized spikes in this infrared signal, making them useful for monitoring geological activities. In addition to volcanoes, other sources of heat include geysers, hot springs, and tectonic uplift regions. Tracking these infrared signatures helps detect early signs of volcanic unrest, such as changes in gas emissions, ground movement, and thermal output before eruptions occur. Satellites use infrared data not only to monitor active volcanoes, but also to create long-term models of heat flow. These models assist in studying mantle plumes, lithospheric thinning, and tectonic stress. Combined with seismic and gas monitoring, infrared data provides a complete picture of geodynamic systems. Nighttime infrared imaging is particularly valuable because, without solar interference, the thermal emissions stand out more clearly against the cooler surroundings. This has proven essential for real-time eruption tracking and emergency responses. The infrared emissions from volcanic zones illustrate how Earth's internal activity radiates energy into space. These invisible photons carry vital information about the geological processes shaping Earth's surface from below. Earth also vibrates with internal gravitational waves, and the resonance from massive earthquakes is recorded globally. When a major earthquake strikes, its effects reach beyond the epicenter. The entire planet begins to vibrate, not just from surface shaking, but also through deep internal gravitational modes. These long-period oscillations, known as free oscillations, can persist for hours or even days, causing Earth to ring like a bell. After a mega-thrust earthquake like the 2004 Sumatra Andaman or the 2011 Tohoku event, seismic waves travel through Earth's interior and trigger gravitational normal modes. These modes involve synchronized oscillations of the planet's mass, including the crust, mantle, and core. These oscillations are detected by highly sensitive seismometers and gravimeters distributed globally. Instruments from networks like the Global Seismographic Network (GSN) register these low-frequency signals, sometimes with periods longer than 20 minutes. The modes are categorized based on their symmetry and depth penetration. Some involve radial expansion and contraction, while others shift mass laterally. Each mode resonates at a specific frequency determined by Earth's internal structure, making them useful for studying the planet's interior. These gravitational waves, not related to astrophysical waves from space, offer insight into how mass and elasticity vary with depth. Analyzing these modes helps improve our understanding of mantle density, core composition, and Earth's overall mass distribution. Repeated observations from different earthquakes show consistent activation of certain modes, indicating that Earth has specific frequencies for internal resonance. The persistence and decay of these vibrations give clues about how deep Earth materials behave under stress. Advanced techniques like frequency domain decomposition and spherical harmonic analysis help isolate and interpret these signals, feeding into global Earth models like the Preliminary Reference Earth Model (PRM). These findings inform updates to seismic hazard assessments. The quiet hum that follows a megaquake, though inaudible, is a measurable phenomenon that represents Earth's internal memory, responding to sudden shifts in energy and mass. These planetary vibrations remind us that Earth is a dynamic, elastic body, continuously responding to the forces at its boundaries. The exosphere interacts with cosmic particles, producing detectable ions. At Earth's outermost atmospheric boundary, the exosphere particles gradually fade into space. Though extremely thin, this layer plays an important role in interacting with the space environment. When cosmic particles enter this region, they can collide with atoms and molecules, creating ions that can be detected by orbiting instruments. The exosphere starts around 500 kilometers above Earth and extends thousands of kilometers outward. It mainly consists of light elements like hydrogen and helium, with occasional traces of oxygen and other atoms. When high-energy cosmic rays, mostly protons and atomic nuclei from beyond the solar system, pass through this region, they strike exospheric atoms. These collisions strip electrons from the atoms, creating ions and producing secondary particles. This interaction is subtle but measurable. Satellites with ion spectrometers, such as those on the DMSP and SWARM missions, monitor ionized particles as part of routine space environment observations. The ion counts fluctuate with solar activity, geomagnetic storms, and cosmic ray flux. Apart from galactic cosmic rays, particles from solar flares and coronal mass ejections also contribute to ion production in the exosphere. During solar events, this particle flux increases, raising the rate of ionization in the upper atmosphere. These ions can drift downward, affecting the ionosphere, or escape into the magnetosphere. Some ions may get trapped in radiation belts, while others contribute to the slow erosion of Earth's atmosphere, a process called atmospheric escape. Modeling these interactions requires understanding both atmospheric density and cosmic ray flux at various energy levels. Space weather models incorporate exospheric ionization as a variable influencing satellite charging, communication systems, and upper atmospheric chemistry. These interactions also play a role in global electric circuits. The movement of ions through Earth's magnetic field generates weak electric currents, contributing to the planet's electromagnetic environment. Though sparse and cold, the exosphere is not inert. It acts as a buffer zone where space and atmosphere overlap, interacting with cosmic particles before they enter the atmosphere. Monitoring ionization in this region provides valuable insight into atmospheric dynamics and cosmic influences, linking Earth's uppermost boundary with the broader space environment. The ionosphere experiences a sudden and uneven increase in electron density, especially near the equator and poles. These shifts influence how radio signals travel. High-frequency signals can be absorbed or reflected in unexpected ways, causing signal fading or complete loss. Systems like GPS, which depend on precise timing signals from satellites, are also disrupted due to unpredictable delays in the ionosphere. One key effect of this is ionospheric scintillation, which causes rapid changes in signal strength and phase. These distortions reduce the accuracy and reliability of satellite navigation, especially during geomagnetic storms, which are most intense near the magnetic equator. To track these ionospheric changes, scientists use ground-based receivers, ionosondes, and satellite-based instruments. Missions like COSMIC, SWARM, and GOLD play an important role in mapping these variations in real time, improving our ability to predict the effects on communication systems. The ionosphere also interacts with atmospheric tides and gravity waves, which amplify its response to solar activity. This complex behavior makes forecasting ionospheric conditions, especially during solar storms, a difficult task. Typically, ionospheric disturbances last for several hours after a solar storm begins. How quickly the ionosphere recovers depends on the severity of the storm and the time of day, with nighttime recoveries often slower due to the lack of sunlight needed for reionization. These disruptions emphasize the importance of incorporating space weather forecasts into areas like aviation, military, and emergency response systems. Real-time alerts now allow operators to adjust communication frequencies or switch to more reliable systems when solar activity causes outages. The ionosphere serves as a critical boundary between Earth and space. When solar activity spikes, it tests the ionosphere's stability, and our dependency on continuous signals makes these invisible fluctuations a global concern. Gravitational tides also affect Earth's rotation, slowly stretching the length of the day by microseconds during lunar cycles. Earth's rotation isn't constant. It changes subtly due to the gravitational forces exerted by the Moon, and to a lesser degree the Sun. These tidal forces cause Earth's solid body and oceans to deform, which in turn slows down the planet's spin. This results in small changes in the length of a day over time, with the average day lengthening by about 2 milliseconds each century. However, short-term variations also occur, influenced by monthly, semi-annual, and 18.6-year lunar cycles. Precision tools like atomic clocks and laser ranging to the Moon confirm that tidal cycles lead to tiny shifts in Earth's rotation, lengthening or shortening the day by a fraction of a second. These tiny changes, while too small to be noticed, are important for accurate timekeeping and for calculating satellite orbits. Additionally, the shifting of mass due to tidal forces affects Earth's moment of inertia, altering the planet's angular momentum and causing minor shifts in the length of the day and in the tilt of Earth's rotational axis, known as polar motion. Scientists track these movements using advanced techniques like very long baseline interferometry, VLBI, satellite laser ranging, and GPS. These tools help detect millimeter-scale displacements in the Earth's crust and microsecond-level shifts in time, allowing for precise modeling of Earth's rotational dynamics. Tidal forces are also a key factor in climate models. The friction between ocean tides and ocean currents can influence the distribution of energy in Earth's climate system. Over millions of years, tidal braking has contributed to the gradual lengthening of Earth's day, from around 21 hours during the Devonian period to the current 24 hours. Even Earth's inner core is involved in this process, as gravitational interactions between the mantle and the core lead to slight movements that further influence the planet's rotation. These interactions are still being studied, as they have implications for understanding deep Earth dynamics and the generation of Earth's magnetic field. Although Earth's day length may seem constant, it is the result of complex planetary mechanics. Tidal forces, acting silently in the background, stretch time itself moment by moment as Earth rotates under the influence of its closest celestial neighbor. The Earth's crust is a thin, floating shell that accounts for less than 1% of the planet's radius. The solid land beneath our feet is a fragile layer compared to the vast depths of the planet. The crust, Earth's outermost layer, is thinner than the skin of an apple in relation to the size of the planet. The crust varies in thickness, being about 5 kilometers thick beneath the oceans and up to 70 kilometers beneath mountain ranges. Meanwhile, Earth's total radius is roughly 6,371 kilometers. There are two main types of crust: oceanic and continental. Oceanic crust is denser, thinner, and younger, primarily composed of basalt. Continental crust, on the other hand, is thicker, less dense, and older, made mostly of granite-like rocks. Both types of crust sit atop the upper mantle, forming a rigid layer known as the lithosphere. The crust floats atop the semi-fluid asthenosphere, a part of the mantle that allows tectonic plates to move. This dynamic balance is similar to how icebergs float on water. Thinner, denser plates sink while thicker, lighter ones rise. Seismic waves provide much of what we know about the crust's structure. When earthquakes occur, the speed and path of these waves reveal boundaries between the crust, mantle, and deeper layers. This has enabled scientists to map variations in the thickness and composition of the crust worldwide. Beneath the crust lies the moho, a distinct boundary where seismic wave speeds change significantly. This marks the transition from the brittle crust to the more ductile mantle below. The crust is continuously recycled over geological timescales. New oceanic crust forms at mid-ocean ridges, spreads outward, and eventually sinks back into the mantle at subduction zones. Continental crust is more persistent, but can be altered by tectonic collisions, volcanism, and erosion. Despite being thin, the crust plays a crucial role in Earth's systems. It supports the biosphere, regulates carbon through weathering, and drives processes like erosion and sedimentation. The crust's composition also influences the formation of mineral resources and energy reservoirs. In planetary science, Earth's crust is an example of a differentiated planetary layer. While other rocky planets have crusts of varying thickness and composition, Earth's plate tectonics make it uniquely dynamic. Studying the crust helps scientists understand how planetary surfaces evolve over time. Despite its thinness, Earth's crust is a vital, ever-changing interface between the deep interior and the cosmos. It floats above a sea of rock in constant motion, fragile, mobile, and indispensable. Deep within the Earth, the core is as hot as the surface of the Sun. Temperatures in the inner core can reach up to 7,000 degrees Celsius. The core lies under extreme conditions of pressure, dense metals, and heat. The inner core, composed mainly of iron and nickel, starts at about 5,160 kilometers beneath the surface and has a radius of approximately 1,220 kilometers. Despite its solid state, the inner core is surrounded by the outer core, a molten convecting layer responsible for generating Earth's magnetic field. This intense heat originates from a mix of residual energy from Earth's formation, radioactive decay of isotopes like uranium and thorium, and heat released as the inner core crystallizes. These processes maintain the core's high temperature over geological timescales. Laboratory experiments and seismic models provide indirect evidence of the core's extreme conditions. By recreating high-pressure and high-temperature conditions, researchers have estimated the melting and solidification behavior of iron under core-like conditions, supporting current temperature estimates. The inner core remains solid because of the immense pressure which raises the melting point of iron. As Earth cools over time, more of the outer core crystallizes onto the inner core, causing it to grow. Seismic waves provide the clearest insights into the inner core's structure. The way P waves travel through the core reveals differences in density and suggests complex layering, possibly even differential rotation compared to the mantle. Understanding the core's heat is crucial to explaining Earth's geological dynamics. As the outer core convects, driven by thermal and compositional gradients, it generates electric currents that create the magnetic field. This magnetic field protects Earth's atmosphere from solar wind and is essential for supporting life on the planet. The heat also influences the behavior of the lower mantle, creating a complex, interconnected system. Heat transfer from the core mantle boundary powers the mantle convection, plate tectonics, and volcanic activity. This deep, invisible thermal engine drives the entire solid Earth system. The properties of the core also affect Earth's rotation and gravitational field. Small irregularities in the mass distribution of the core cause slight wobbles and long-term changes in the planet's spin axis. While core-mantle interactions play a key role in geodynamic evolution, they also impact Earth's physical behavior. At the heart of our planet, far beyond our reach, lies a solid metal sphere, heated to solar-like temperatures. This serves as a reminder that Earth, although stable on the surface, remains thermally and dynamically active from its innermost layers outward. When solar particles travel through Earth's atmosphere, they generate currents that affect both weather and electronics. Upon reaching Earth, these charged particles don't always stop at the magnetosphere. Some particles penetrate the atmosphere, particularly near the poles where the magnetic shielding is weakest. As they move downward, they create electrical currents that impact both climate and electronic systems. These particles, mainly protons and electrons, originate from solar flares and coronal mass ejections. Upon entering the upper atmosphere, they ionize atmospheric gases, especially in the thermosphere and stratosphere. This ionization boosts conductivity, allowing large electric currents to form. One of these current systems is the auroral electrojet, which flows horizontally through the ionosphere and strengthens during geomagnetic storms. These currents change the electric potential across the polar atmosphere, affecting how energy and momentum are transferred within the system. As solar particles dive deeper, they can create vertical currents between the ionosphere and the ground, a process tied to the global electric circuit. These currents alter the distribution of atmospheric charge and may affect cloud formation, precipitation patterns, and pressure systems. However, the exact mechanisms of these effects are still being studied. Alongside the climate, these particle-induced currents also affect technology. During intense storms, they can induce geomagnetically induced currents, GICs, in power grids, pipelines, and railways, which can damage infrastructure and cause voltage instability. Satellites and high-altitude aircraft are also at risk. Charged particles can disrupt onboard electronics, change satellite orbits due to atmospheric drag, and increase radiation exposure for crews and passengers at high latitudes. Space weather advisories often recommend adjusting flight routes during significant solar events. Cosmic ray muons, produced when high-energy solar particles collide with atmospheric nuclei, also reach the surface and are useful in particle physics and geophysics. Their variation during solar events offers another tool for studying space-atmosphere interactions. Recent atmospheric models incorporate particle precipitation data from missions like POLSI and Theus. These inputs help refine our understanding of polar atmospheric dynamics, ozone chemistry, and how space weather interacts with Earth's climate. The penetration of solar particles into the atmosphere sets off a complex chain of events, from electrical imbalances to shifts in atmospheric conditions. Their presence highlights how deeply solar activity affects Earth's environment, beyond just space and into the air we breathe. Earth's magnetic field, which naturally fluctuates, experiences reversals and weaknesses that have been documented by satellites and geologists. Earth's magnetic field is not fixed. It undergoes changes over time. The field's structure experiences natural oscillations, including variations in strength, the movement of the magnetic poles, and even complete reversals of polarity. Satellite observations and geological records have confirmed that the magnetic field is dynamic. The magnetic field is generated by the movement of molten iron and nickel in Earth's outer core, driven by heat and rotation. This movement powers the geodynamo, which maintains the field's structure, but also introduces instability over long periods. A striking feature of this instability is geomagnetic reversal. During these events, the north and south magnetic poles swap places. Geological evidence shows that such reversals have occurred numerous times in Earth's history, with the most recent full reversal happening around 780,000 years ago. These reversals unfold over thousands of years, during which the field weakens and becomes highly irregular. Satellite missions like ESA's Swarm and NASA's CHAMP have mapped the present-day magnetic field structure in detail, detecting regional anomalies like the South Atlantic anomaly, an area where the field is unusually weak and exposes satellites to increased radiation. This region appears to be expanding, drawing the attention of scientists. The magnetic field also experiences secular variation, meaning gradual changes in its intensity and structure. For example, the magnetic North Pole has migrated more than 1,000 kilometers in the past century, and this rate of movement has accelerated in recent decades. These shifts reflect ongoing changes within the Earth's core. Paleomagnetic data from lava flows, ocean sediments, and archaeological materials provide a record of past magnetic field behavior. These records show that magnetic reversals and excursions, temporary partial flips, are irregular but occur roughly every few 100,000 years. The mechanisms behind reversals are not fully understood, but models suggest they are caused by instabilities in the core's convective flow. As flow patterns change, the dipole component of the magnetic field weakens, temporarily being replaced by more complex multipolar structures before the dipole re-establishes with reversed orientation. Changes in the magnetic field affect more than just navigation. A weaker magnetic field allows more cosmic radiation to penetrate the atmosphere, which can impact satellite electronics, radiation exposure, and atmospheric chemistry. Understanding these changes is vital for preparing for future space weather impacts. Earth's magnetic field is a living system, shaped by both internal motion and external forces. Its variations are slow and vast, deeply connected to the planet's thermal and rotational dynamics. In space biology, certain microorganisms, such as cyanobacteria, have been tested for their ability to survive the vacuum of space. These microscopic organisms, known for their resilience on Earth, can endure harsh environments such as hot springs, deserts, and even the upper atmosphere. Their strong cell walls, efficient DNA repair mechanisms, and metabolic flexibility make them ideal candidates for astrobiological testing. Experiments conducted aboard the International Space Station and satellites like EXPOSE on ESA's Columbus module expose cyanobacterial samples to vacuum, cosmic radiation, ultraviolet light, and extreme temperatures. Despite these conditions, many of the cells recovered metabolic function after rehydration and protection from direct radiation. These tests simulate what microorganisms might experience on Mars or during interplanetary travel. The survival of these microbes suggests that some life forms could endure space travel, possibly even inside rock fragments, an idea known as lithopanspermia, which suggests that life could travel between planets on meteorites. These findings have implications for planetary protection policies. As life could survive in space, missions to other planets must be cautious to avoid contaminating alien ecosystems. Furthermore, these resilient microbes could potentially be used for life support in space habitats. Cyanobacteria can produce oxygen and recycle waste, making them useful in closed-loop systems for long-duration space missions. While the survival of these organisms doesn't confirm life beyond Earth, it expands the possibilities of where life might exist. In studying Earth's magnetic field, we see that even small changes in the planet's core and surface can have significant effects on the environment, our technology, and even the potential for life elsewhere in the universe. These subtle forces shape not just our planet, but also the broader dynamics of the solar system. Changes in the resonance frequencies can be measured when the size and conductivity of the atmospheric cavity shift. Studies show a link between changes in Schumann resonance amplitude and solar activities like sunspots, solar proton events, and geomagnetic storms. Although these changes are subtle, sensitive monitoring stations using extremely low-frequency ELF antennas can detect them. Since the resonance frequencies depend on the size and conductivity of the atmospheric cavity, shifts in these properties caused by solar radiation result in slight global changes. For example, during geomagnetic disturbances, the frequency bands can expand and their amplitudes can increase or decrease depending on the location and time of day. Schumann resonances are also influenced by lightning frequency and distribution, which can be affected by climate conditions and long-term solar cycles. This makes the system a useful tool for studying both space weather and global atmospheric changes. Ground-based observatories worldwide contribute to an ongoing collection of data about these resonance behaviors. These observations not only aid in atmospheric science, but are also used to monitor climate variability and examine ionospheric disturbances. Unlike artificial electromagnetic sources, Schumann resonances naturally occur and affect the entire globe. Their interaction with solar inputs highlights how low-frequency terrestrial phenomena are connected to space weather dynamics. These resonances demonstrate that the atmosphere isn't passive, but responds to both internal and external forces, including the constantly changing output from the sun. The atmosphere also generates gravity waves, which are fluctuations visible in weather and satellite data. Gravity waves in the atmosphere are different from gravitational waves in space. Instead of being ripples in space-time, gravity waves are ripples of air created when buoyant forces try to restore displaced air masses to equilibrium. These waves travel through the atmosphere, transferring momentum and energy. They become especially noticeable in Earth's thinner high-altitude layers. Atmospheric gravity waves form when stable air is disturbed by mountains, weather systems, or convection. As the air rises and falls, buoyancy and gravity interact to create oscillations that spread horizontally and vertically. In the upper atmosphere, where the air density is low, gravity waves can grow to large amplitudes. Satellites observe these waves through patterns in clouds, air glow brightness variations, and temperature fluctuations in the mesosphere and thermosphere. Instruments on missions like TIMED and ICON capture these structures with high-resolution imaging and spectral data. Gravity waves play an important role in the vertical exchange of energy between atmospheric layers. As these waves move upward, they carry energy from the lower atmosphere to higher altitudes, affecting wind patterns, temperature distributions, and ionospheric behavior. In the thermosphere, these waves can travel at speeds of hundreds of meters per second. When they break, like ocean waves, they release energy and momentum, causing localized turbulence and altering circulation. These effects are especially pronounced near the equator and the polar regions. The presence of gravity waves in satellite data helps scientists understand atmospheric drag, which impacts satellite orbits. During storms or solar disturbances, increased gravity wave activity can lead to higher atmospheric drag, shortening satellite lifespans or changing their trajectories. Meteorological models also consider gravity wave dynamics to enhance weather predictions. These waves influence jet streams, cloud formation, and storm development, especially in regions like mountains and tropical areas where gravity wave formation is most common. High-altitude balloon measurements, LiDAR systems, and sounding rockets complement satellite data to create a more complete picture of how gravity waves interact with other atmospheric processes, including tides and planetary waves. Gravity waves reflect the dynamic nature of the atmosphere. Even in its thinnest layers, the air is constantly moving in response to terrain, weather systems, and solar energy inputs. These waves offer a glimpse into the invisible architecture of the atmosphere. Understanding them is vital for climate models, satellite mission planning, and predicting how Earth's atmosphere responds to both terrestrial and cosmic forces. Satellites have also detected magnetic structures beneath mountainous regions. These magnetic rings are unusual, closed-loop variations in Earth's magnetic field, believed to be caused by localized geological features combined with crustal magnetization. They interact with cosmic and solar radiation and have been identified through precise magnetometer readings from satellite missions like SWARM. These instruments detect small deviations in the geomagnetic field due to differences in rock composition, mineral alignment, and tectonic history. In some high-relief terrains, these differences form patterns that resemble magnetic loops or arcs. These rings are typically found in large mountain belts, where geological processes have altered the magnetic properties of subsurface rocks. High-pressure metamorphism, remnant magnetization, and tectonic deformation have contributed to their formation over millions of years. What makes these magnetic rings particularly interesting is their interaction with space weather. During geomagnetic storms, these loops can focus incoming charged particles, enhancing local ionization in the upper atmosphere. This can lead to increased auroral activity, radio interference, or even regional ground currents. The cosmic ray flux is also affected by these structures. Studies suggest that magnetic loops in the crust can influence how energetic particles penetrate Earth's surface environment, impacting secondary particle showers and radiation measurements at ground level. Researchers are exploring these interactions by comparing satellite magnetic maps with cosmic ray detectors and atmospheric sensors to understand how these subsurface anomalies connect with Earth's broader electromagnetic system. These magnetic rings don't act as isolated sources of magnetism, but instead as distortions in the ambient geomagnetic field. Their circular or elliptical shape may enhance their ability to trap or deflect charged particles under certain space weather conditions. Understanding these anomalies sheds light on the lithosphere's dynamics and helps refine global geomagnetic models. It also aids in interpreting magnetic signatures during planetary exploration, where similar crustal features may exist on the Moon or Mars. These ring-like structures beneath mountains illustrate how geology and space physics intersect, subtly influencing the behavior of Earth's magnetic shield. The ozone layer, often seen as a stable protective shield, is actually very dynamic. Satellite observations have revealed that the ozone layer undergoes pulsing variations in response to solar events, in addition to seasonal cycles and atmospheric transport. These pulses show as temporary thinning or intensification of ozone at specific altitudes. The ozone layer mainly resides in the stratosphere, between 15 and 35 kilometers above the Earth's surface. It forms when solar ultraviolet radiation splits oxygen molecules, allowing ozone ODAs to form. This same radiation also regulates its density and vertical distribution. During solar storms, increased X-ray and UV radiation penetrate the upper atmosphere, triggering chemical reactions that break down ozone molecules, particularly at high latitudes. This results in temporary thinning or redistribution of ozone, detectable in satellite measurements. Missions like Aura, Sentinel-5P, and Suomi NPP have recorded these pulses as short-term dips in ozone levels, which often recover within days or weeks. These pulses vary depending on the hemisphere, solar cycle phase, and geomagnetic conditions, making them valuable indicators of Sun-Earth interactions. The pulsing behavior is also connected to atmospheric waves and tides, which move ozone-rich or ozone-poor air across latitudes and altitudes, creating layered patterns that rise and fall in sync with both terrestrial and solar forces. In some cases, ozone levels increase rather than decrease, particularly when polar stratospheric warming forces ozone-rich air downward. These upward and downward pulses show the complexity of the chemical and dynamic coupling in the middle atmosphere. Tracking these fluctuations is essential for understanding the ozone layer's health and its role in absorbing harmful UV radiation. It also helps with climate modeling, as ozone affects stratospheric temperature and circulation patterns. Satellite instruments like ultraviolet spectrometers and microwave limb sounders are used to track ozone density over time and space, assisting in modeling natural variability and anthropogenic trends, especially in light of international ozone recovery agreements. These pulsing ozone belts are not anomalies. They're part of a living atmospheric system, responding directly to solar activity and providing a chemical record of space weather events that ripple through the stratosphere. Satellites have detected rare traces of molecules from outside the solar system. These gases, usually carried by micrometeorites or cosmic dust, enter Earth's atmosphere at high speeds and remain only briefly before dissipating. Instruments aboard missions like NASA's AAM and ESA's Odin have recorded these rare detections of molecules such as carbon monoxide, ammonia, and complex organics at mesospheric and thermospheric altitudes. While these detections are short-lived, they provide valuable insights into the exchange between space and Earth's atmosphere. These molecules come from interstellar dust grains and cometary debris that occasionally reach Earth's atmosphere. As they enter, they experience frictional heating, causing them to release both terrestrial and non-terrestrial gases. Some of these molecules survive long enough to be identified spectroscopically before breaking down due to solar radiation or reacting with native atmospheric species. Detection is possible through high-resolution ultraviolet and infrared spectroscopy. By studying the absorption and emission patterns, scientists can distinguish between local atmospheric gases and those that come from outside Earth. These signatures are subtle but noticeable, especially when looking at isotopic ratios that are not typically found in Earth's atmosphere. The detection of such gases supports the idea that Earth remains chemically open to space. Even today, the upper atmosphere continues to receive inputs from the broader cosmic environment, a continuation of the processes that have shaped the planet since its formation. These findings also help planetary scientists understand other planets. Similar detection methods are used to study the atmospheres of Mars, Venus, and Titan, revealing the role of external chemical influences and their importance in atmospheric chemistry and potential habitability. Some of the detected compounds, such as amino acid precursors, are biologically relevant. Their short presence in Earth's atmosphere highlights the possibility that cosmic contributions may have played a role in prebiotic chemistry. While these compounds don't last long enough to reach the surface intact, ongoing observations are refining the detection limits and improving models of atmospheric mixing and reactivity at high altitudes. Although detecting interstellar molecules is not a common occurrence, it shows that Earth's atmosphere is permeable. Even at the edge of space, Earth interacts with the galaxy. These transient visitors, molecules from beyond the solar system, leave chemical traces that tell the story of Earth's connection to the cosmos. Bacteria living on geogenic hydrogen survive deep beneath Earth's surface, at depths of over 2 kilometers without sunlight. In the absence of light and photosynthesis, microbial life thrives by consuming hydrogen generated through natural geological processes. These bacteria inhabit fracture zones and rock pores deep underground, relying on a form of chemical energy that is independent of surface life. The primary energy source for these bacteria is geogenic hydrogen, which is produced by radiolysis, a process where background radiation from elements like uranium, thorium, and potassium breaks down water molecules trapped in rock. The released hydrogen fuels deep microbial ecosystems. These subsurface microbes, mostly anaerobic bacteria and archaea, use hydrogen through chemolithotrophic pathways. They use it to reduce sulfate, carbon dioxide, or other electron receptors, producing methane or other simple compounds as byproducts. These ecosystems are found in deep mines, boreholes, and ancient aquifers. In locations like the South African gold mines and the Canadian Shield, microbial colonies have been found living in isolation for millions of years. Their genetic material shows adaptations to high pressure, low nutrients, and minimal energy flux. The existence of such life challenges traditional ideas about habitability. These microbes don't rely on sunlight, oxygen, or surface-derived organic material. Instead, they are supported by Earth's internal heat and radioactive decay, representing a biosphere powered from below, not above. Hydrogen-fed bacteria have significant implications for astrobiology. If similar geochemical processes occur on other planets or moons, such as Mars or Europa, they could support microbial life beneath their surfaces. Earth's deep biosphere serves as a model for understanding extraterrestrial habitability under extreme conditions. Methods to detect these microbes include drilling, deep sampling, and genetic sequencing. Cultures taken from deep rocks show extremely slow metabolism, but remain viable and capable of growth when the right conditions are provided. Their survival strategy focuses on efficiency and resilience, rather than rapid reproduction. These ecosystems also play a role in Earth's deep carbon cycle, fixing carbon into biomass or releasing methane. They influence long-term geochemical balances between Earth's interior and surface. The discovery of geogenic hydrogen-based life changes our understanding of where and how life can exist. It extends the concept of a biosphere far beyond the sunlit zones into a hidden realm powered by the planet's own energy. Earth's internal heat flux averages about 0.09 watts per square meter, a continuous geothermal output from radioactive decay. Beneath the surface, heat rises toward the crust, a form of geothermal energy primarily driven by the decay of long-lived isotopes like uranium-238, thorium-232, and potassium-40 in the mantle and crust. As these isotopes decay, they release energy as heat, which slowly moves upward through conduction. Geothermal heat is fundamental in driving tectonic activity. It powers mantle convection, which moves tectonic plates, forms volcanoes, and triggers earthquakes. This internal energy also helps maintain Earth's magnetic field by fueling fluid motion in the outer core. Measuring Earth's heat output involves both direct measurements in boreholes and indirect estimates from surface heat flow maps. These studies show variation across regions, with higher heat flux near tectonic boundaries and volcanic zones, and lower flux in ancient stable continental areas. On average, Earth releases around 44 terawatts of geothermal energy, about twice the amount of energy consumed globally by humans. However, this energy is spread thin across the planet's surface, making it imperceptible without specialized instruments. The geothermal gradient, the rate at which temperature increases with depth, averages about 25 to 30 degrees Celsius per kilometer in the upper crust. This makes deep rock layers significantly hotter than the surface, allowing geothermal energy to be harnessed for electricity and heating in specific locations. This constant flow of heat also sustains deep microbial life. In some ecosystems, heat and chemical energy from rock-water interactions support microbes kilometers below the surface, independent of sunlight. The geothermal signal remains remarkably stable over geological timescales, with only a slight decrease as radioactive isotopes decay over billions of years. Its persistence ensures that Earth remains geologically active and thermally dynamic. Understanding geothermal heat helps model planetary evolution and compare Earth with other rocky bodies. Mars, for example, shows evidence of past geothermal activity, but has largely cooled, highlighting the uniqueness of Earth's ongoing internal energy. Even without visible volcanic eruptions or tectonic movements, the planet continues to emit thermal energy, shaping Earth's surface and internal behavior. Magnetic pulses recorded during solar eclipses show subtle oscillations in Earth's magnetic field. During total eclipses, magnetometers around the world have recorded these small but measurable variations in the magnetic field. These temporary pulses, lasting minutes to hours, offer a rare opportunity to study the coupling between space and Earth's atmosphere under changing solar conditions. The primary cause of these changes is the sudden drop in solar radiation during the eclipse. As the moon blocks the sun's light, ionization in the upper atmosphere decreases rapidly, particularly in the D and E layers of the ionosphere. This reduces electrical conductivity and alters the ionospheric current systems, causing weak geomagnetic variations. These effects are most noticeable near the eclipse path, but are also observed at distant magnetometer stations. This phenomenon is referred to as the eclipse effect in geomagnetism. It includes a mix of reduced solar-driven currents and dynamic responses in Earth's magnetic environment. The amplitude of these pulses varies, ranging from a fraction of a nanotesla to several nanoteslas, depending on location and conditions. Research teams have used dense networks of ground-based sensors and coordinated satellite observations during past eclipses, such as those in 1999, 2001, and 2017, to track these electromagnetic responses. The eclipse shadow acts like a switch, rapidly turning solar input off and on. This allows researchers to observe how Earth's magnetic system adapts to sudden changes. These measurements also help improve the resolution of magnetospheric and ionospheric models. Understanding these transient responses during eclipses improves predictions for more complex events like geomagnetic storms. While the magnetic pulses from eclipses are not powerful enough to disrupt electronics or navigation, they reveal the delicate balance between solar radiation and Earth's electromagnetic environment. The eclipse momentarily disrupts the usual solar ionospheric balance, and Earth's magnetic field reflects this brief interruption, offering a silent global fingerprint of the sun's absence.